You get a volunteer for opening prayer? Make me do it today? Go ahead, Mark.
Dear Heavenly Father, thankful for this day, so they can be here on campus to learn. We ask you to bless us and help us to stay healthy, and bless us that we'll be able to understand these transport principles. In the name of Jesus Christ, amen.
Amen. All right, so quick announcement. So I sent you an email late last night about update to the schedule. So we're continuing to sort of move on in this material, and I looked at what we were doing, and we're behind where Bill's schedule was. I guess I can't move as fast as he does. So I cut out an exam. So I don't know if you guys like that. You're welcome if you do. So far. So and I like that a little better when I was looking at the schedule when we were first setting it out. I thought it was kind of funny where the exam was placed. So this way we'll get through the equations of change up through mass transport, and then we'll take an exam, and we'll solve a bunch of stuff, and then we'll take the final. So I think that should be nice. Hopefully that makes our lives a little easier. So we'll continue on today with vectors and tensors. Last time I called it lecture 1, but then we did 2 lectures on it. So now I'm calling it lecture 3. So if you want to go back in your notes, if you're on a new label, you can call what we did last time lecture 2, where we started. So today I'm going to call this one lecture 3. And we're going to start out and talk about coordinate systems, and then we're going to talk about how to do some algebra and calculus in these curvilinear coordinate systems. So so far we sort of had talked about all of this stuff we've been doing sort of without thinking about the coordinate system. And everything we've done so far rigorously for sure applies to Cartesian coordinates, which we'll define in a second, and make sure we're all on board with. And we're going to see some subtleties that come in when we talk about curvilinear coordinates. And then we're going to point out some additional subtleties that exist in even more complicated coordinate systems, but we won't work with those in this class, but I just sort of want to make you aware of them. So if you remember, we said that coordinate system, I'm just going to use this so I don't have to write coordinate system all over the place. A coordinate system is a choice of basis vectors for our vector space. Which in this case, right, is R3, mostly is the one we care about, 3-dimensional space. So for example, if we're going to use delta 1, delta 2, and delta 3 as our basis. So if I pick these 3 basis vectors to be x, y, and z, that's the Cartesian coordinate system. Okay, so this is the familiar Cartesian coordinate system. Okay, and remember that we said it was the natural basis for R3, right? It's the one that's along a sort of 3 principal directions, so that was easy to do. So we might think, why have the rest of the discussion, right? Like, why define more complicated coordinate systems? Like, we have an easy one, okay? It's the natural one. That seems like we would just stick with that. That's a fair question. So I can think of 2 reasons why we care. So maybe I'll put this, why not stop here? I'll just go home and move on. Okay, so there's 2 reasons I can think. The first is, believe it or not, mathematical convenience. Okay, so if you're trying to solve a problem with a certain geometry, suppose for instance we're trying to find the drag on the sphere, and we have to resolve the velocity field around that sphere. It's actually a lot more complicated to come up with that solution. Sometimes not even possible to find an analytical solution if we're using a Cartesian coordinate system. But by switching coordinate systems, life gets a lot easier. We can do things like a separation of variables or some other piece, okay? And then we can come up with, you know, our solution. And so, you know, it's actually, even though we have to do a little bit of work, it's actually more convenient than the problems we can solve. Okay, so that's one reason. A second reason is physical understanding. Okay, and this one's a little maybe more abstract, but think about the idea here of if I did something like if we just talk about polar coordinates, right? And if I wrote down x squared plus y squared equals r squared, right? You know that that's a circle, but that's because you got taught that that was a circle and you've looked at it a lot of times, right? But if I did polar coordinates and I said, you know, r equals r, right? Now it's much more clear to you, right? Oh, that's just a circle, right? And so similar kinds of things happen in these more complicated curvilinear coordinate systems, right? The solutions that we get out are expressed in variables that we more physically, you know, intuitively understand. So that's another reason for doing this. So those are two reasons I could think of why we torture graduate students with coordinate systems. So the next thing I'm going to talk about is classifying coordinate systems and the different ways that we might go about doing that. So I am going to write, let's see, so different, let's talk about linear versus homogeneous first. We'll talk about linear first, and then we'll do. Okay, so linear coordinate system is a system where there's a one-to-one linear mapping with the Cartesian system. Okay, so I'll write that out. So 1-to-1 linear mapping with Cartesian. Okay, and we'll actually see how that manifests, and you can see that in your book, actually, what I pointed out to you, hopefully become more clear. All right, what that means is we can take the basis vectors of the coordinate system that we care about, and we can express it as a matrix multiplied by the Cartesian coordinates. Okay, so there's this linear mapping that we can go back and forth. So that's a linear coordinate system. In the class, we won't ever deal with a nonlinear one. They're actually kind of crazy. It's kind of a really weird coordinate system to want a nonlinear coordinate system. So almost everything I bet you'll ever encounter will be linear coordinate system. Homogeneous coordinate system is a system where the basis vectors are constants throughout the domain. Right, and we will definitely deal with cases that are not that. So these are the basis vectors are constant. And this is going to be in contrast to a curvilinear coordinate system where the basis vectors are a function of space. Okay, so that means that in a Cartesian coordinate system, if you just imagine for a second, we're at a three-dimensional space, the x direction always points in the x direction, right? It's always whatever, like let's say that's x, it's always x, no matter where in space. But we're going to give an example of, say, cylindrical coordinates, right? And in cylindrical coordinates, if I'm in this part of space, r might be this direction if I'm the origin, but over here, r is in that direction. Right? So r, the basis vector, changes as a function of space. Theta, the same thing, right? So theta is this way, but over here it's this way, over here it's this way. Now it changes as a function of space. So, you know, spherical and cylindrical coordinates, I'll give examples here in a second, but spherical and cylindrical coordinates are curvilinear because their basis vectors are a function of space. Okay, another property is orthogonal. Okay. And in an orthogonal case, the basis vectors have the following property. So the basis vectors obey delta I dot delta J equals 0 when I is not equal to J. Okay, so we'll give some examples of that, but think about X and Y, they're at right angles, right? So, I do delta X dot delta Y, the unit vectors, and I get 0. Okay. Another property would be a normalized. In normalized, I get basis vectors are unit vectors. Okay, which means that delta I dot delta I is equal to 1. Okay, so as opposed to being not normalized, I could, if I have the unit vector dotted with itself, it could be, 7 or whatever, right? So the normalized unit vector has that property. If something is both orthogonal and normal, which is a property that sometimes happens, then it's called orthonormal. Heaven forbid we say orthogonalized normal. That sounds ridiculous. We must say something shorter. Okay. Last two properties are right-handed. Okay. Right-handed obey the right-hand rule in the cross product. Okay. So if I do delta X cross delta Y, I get delta Z. Fix that. Z. Okay. So this would be something like, I was just trying to draw these, make sure. I want to do it the way. Okay, X, Y, Z, right? Right-hand rule. Okay. Left-handed coordinates obey delta X cross delta Y is equal to minus delta Z. And that happens if you draw your coordinates like this. Right? So sometimes you go to write down a three-dimensional coordinate system and you're like, oh, I make X, Y, and you draw a Z out the back. Okay, and you forget, okay, and that's actually left-handed. So if you try to do that, X cross Y and give you positive, and that would come out of the board. So that one's left-handed, X cross Y into the board. Okay, so those are properties of coordinate systems. So I'm going to give some examples, and then I'll take questions if it's still clear. Okay, so here are some. So first one is Cartesian. Okay, and Cartesian we've got, I make that one delta X, that one delta Y, that one delta Z. That's right-handed, right? So, okay, so Cartesian there. This one is homogeneous, okay? So homogeneous, I'm just going to write the letter. You can write it all out, but I'm kind of running out of space. Homogeneous, it's orthonormal. Orthonormal. Okay, and it's right-handed. I miss anything else? Yeah, they're all linear that I'm going to do examples on. Okay, so that one's easy. Next one, here's a kind of fun example. So if I make my basis here delta X, delta Y, and I make it off the Z-axis like this, and I'm going to call this delta alpha. This was called the oblique coordinate system. Okay, so this one had, coordinates X, Y, Z. This is going to have an X, Y, alpha. Okay, and this one is homogeneous. It is called skew, Okay, skew is when I'm not orthogonal, so not orthogonal is skew. Okay, but it is normal. Okay, normalized, and it's right-handed. Okay, yeah.
Is that delta alpha, is it pointing like normal to the x and between the y and the z?
Normal to the
Like is it on the y?
you're using normal as a, is it orthogonal?
Orthogonal, yeah.
Yeah, so it's normalized, maybe that's what I want to say. So it's not, there's some angle here, alpha or something, or theta from that direction, but that's our direction's always off kilter. So these are right angles here, right? But this is not a right angle there.
Right. But is it on the y, z, if there was a z?
Oh, you're asking if it's in the YZ plane?
Yeah.
Yes. But I don't think it necessarily has to be. You could also have some other coordinate system, right, that moves over. But I think in the oblique coordinate system. Yeah. Okay. So this one's kind of weird. Okay, I'm just trying to generate some examples. So like we don't often solve problems in the oblique coordinate system, but I wanted to give you an example of something that was not orthogonal. A couple more examples, more familiar ones here. So this one, if I have delta R and delta phi, and up here I have delta theta, okay? This defines the spherical coordinate system. Okay, and the spherical coordinate system is curvilinear. Okay, so I'll write curvilinear for that. All right, so it, that basis vectors depend on space, but it's orthonormal. Orthonormal, and it is right-handed. So we're good with that. We have cylindrical. And then cylindrical coordinates, we have some delta R in the plane, right? And some vector delta theta. And then we have delta Z. Okay, and it has the same properties as spherical. It's curvilinear, orthonormal, and right-handed. Okay, I have two more examples, and then I'll stop and take some questions. It's all up here. Okay, this one, we're going to test my drawing skills, which will probably result in a bad grade. Let's see. This one, I've got, I'll draw my easy one, a delta Z here, and then I have a delta V along that axis and delta U along that axis. Okay, so this is an ellipse. So this is going to be my elliptical coordinate system. And this is perpendicular to the ellipse. So if you've ever seen like an elliptical orbit, and then these are like tangents to it, like field lines. Like if you've ever seen like two magnets, okay, that's kind of what this other one is. It's just a something that's orthogonal to that. Okay, so this is an elliptic coordinate system, and it is curvilinear. It's orthogonal. Okay, so hopefully you can see that those are orthogonal to each other, but it turns out it can't be normalized, so it's not normal. Okay, non-normalized. And I couldn't find out for sure, but I'm almost positive it's right. Okay. Last example is somewhat similar. This one is parabolic. So here I've got a parabola in the plane, and then something that's orthogonal to the parabola. And so this one here is I think they call that delta tau. And this is along this one here, that's a delta sigma. Then we have delta z again. So these are like parabolic cylindrical and then elliptical cylindrical. You can kind of see how they're like cylindrical because delta z is still in there. So this is a parabolic coordinate system, and it is also curvilinear or orthogonal and right-handed, but not normal. Okay, so mostly in the class, right, we're going to use the ones you're familiar with, Cartesian, cylindrical, and sphericals. But I wanted to give you some idea about a broader perspective on coordinate systems. The sort of these properties, and you can kind of see this with the parabolic and the elliptic, the property of orthogonality is really important. And we'll see that if you take that property away, stuff gets messier. For the most part in engineering and in transport, you deal with linear and then either homogeneous or curvilinear coordinates that are orthogonal. And occasionally get some that aren't normalized, so, and mostly right-handed. Okay, the ones that are not orthogonal get messy. But the reason people care about them is because of general relativity. So in general relativity, space becomes part of the equations, okay? And now you have to think about coordinates in a way in which the actual dimensions of space are changing. And that's where you can start to get things that are nonlinear. You can start to get things that are certainly not orthogonal, okay? And so when you guys, really dig into that, right? Okay, you're not going to do that, right? But that's just sort of an idea. So there's a whole field of differential geometry where you write down differential equations about how space itself is changing as a function of time, okay? And if you think about that for a minute, you're like, I'm glad I'm not in that class, I'm in this one, right? Okay, and so that's when the coordinate systems get really messy. But sometimes when you go to look and read about stuff, you'll see some stuff on differential geometry, and that'll sort of, maybe make your brain explode. And so sort of know, like that's where people are coming from, right? The physicists who care about field theory and general relativity and stuff, they've developed a set of mathematics for that. And you don't want to wander too far in that field. There's monsters there, right? Or whatever, right? So, okay. Questions about what I've put up here? Yes.
Are we ever going to use elliptic or parabolic coordinate systems in this class?
I don't know for sure, but like elliptic coordinates are really useful when you have orbits, right? So if you have two things that are moving around each other, elliptics are really useful. Parabolic coordinate system, I can't remember the example I looked up. So I don't think we have anything on that in elliptic, but like you might encounter it if you take like a quantum mechanics class, or if you're in astronomy or something, but I doubt you're going to do astronomy. But more in chemical engineering, right? We're doing, we often care about atoms and molecules, and then we care about orbits, and so you might see something. So I don't know. I wanted to give you a flavor for what was out there, sort of as an introduction, right? And then if we don't use it, we don't use it. But I'm not going to plan on trying to use it just because it's there. But I want to. This was also like, I was reading a little bit and I wanted to understand a little bit of the background of this stuff. So maybe you just got a little bit of interesting. Okay. So I'm gonna, so if you think about it here, homogeneous are sort of a special case of the curvilinear coordinates, right? Like if you can do it for curvilinear coordinates, you can get back homogeneous. Okay. If we assume orthonormal, we're going to be mostly pretty good. Okay. And so we're going to talk about the algebra and calculus of curvilinear coordinates, where we're going to basically assume orthonormal, curvilinear, and then we can sort of go on. And that covers a big case. And Berkshire and Lightfoot cover this in depth with cylindrical and spherical coordinates. And then they have a section at the end where they basically say, assume we remove the property of normality, okay, that we normalized. Okay, and that's that little section where you see all the H's, okay? And all those H's are carrying around this extra dot product from everything. So there's an H alpha, which is the delta alpha, H beta, gamma, et cetera, for the 3 different dimensions. And so they've generalized that for you. So if you have to do something in elliptic coordinates, okay, you can plug those into those formulas and work it out. All right. But we're going to stick with the orthonormal ones for now. And so we're going to start out and let's remind ourselves about cylindrical and spherical coordinate systems. Okay. So to define the coordinate system, we need to define the basis vectors. So I showed you examples of the basis vectors, but let's be a little more rigorous about defining the basis vector. So to define coordinate basis, okay, we define a space curve. F1 is F1 of X, Y, Z. F2, function of X, Y, Z. F3, function of X, Y, Z. Okay, so I'm going to define these 3 curves, okay? And you can see them here, right? Like I drew an ellipse, okay? And that's something that's normal to an ellipse. Right? So we need to define these curves as they go throughout space, right? So maybe you might think for Cartesian coordinates, these look just like a grid, like this, right? And our basis vectors are going to be tangents to those curves, okay? So that's Cartesian. But different coordinate system, right, might have, you know, curves that look like that, something crazy, okay? And now our basis vectors are going to be, you know, the tangents to those curves, all right? So we know what these are already for cylindrical and spherical coordinates, so let's read them up there. Maybe I need to reload. So with cylindrical, spherical, I have R is equal to positive square root of X squared plus Y squared. And then theta is equal to the arctangent of Y over X. And Z is equal to Z. Over here, R is equal to the root of X squared plus Y squared plus Z squared. And I have theta is equal to the arctangent of the root of X squared plus Y squared divided by Z. And then phi is equal to the arctangent of Y over X. Okay? So if you say, for example, look at the cylindrical coordinates, right? This defines, I'll just look in the XY plane, right? This defines polar coordinates, which we know. There, right? And what we want is to have, you know, this be delta R, and that guy be delta theta, right? So we've defined these curves, right? And now we're going to get delta R and delta theta, and we do that by looking at the tangents. So the basis vectors I said, are the tangents to these curves. Okay, so I can, if I write down this vector function f, which is, if I invert it, if I have x f1, f2, f3, delta x plus y of f1, f2, f3, delta y. Oh, it's kind of a mess to write this, but hopefully we won't spend too much more time on this part of the math here. Plus z, which is a function of f1, f2, f3, delta z. Okay, so now I'm going to say, how do I get the tangents? I get the tangents by looking at delta f divided by delta fi. Okay, and so these fi's, right? These are theta z's. Okay, and my unit vector delta is a normalized version of that. Ui divided by the norm of ui. Okay, so this is just a way to get the tangent, right? But then it might not be normalized, and then we normalize it. Okay, so we can practice this. We'll do an example. And then these, I didn't write these up here, okay, but this x, f1, f2, f3, this is the inversion of these, okay, which is probably the more familiar form to write them, right? Like, that's where you write x equals r cosine theta, and y is r sin theta, for example. All right, so let's do an example just to see this in some. So, f is, like I just said, r cosine theta delta x plus y is r sine theta delta y plus z delta z. Okay, so now to find, say, u theta, I need to take df d theta. F. Okay, so when I do that, I have to take the derivative of that guy and the derivative of that guy, right? This one's going to go away. The derivative of r cosine theta is minus r sine theta delta x plus r sine theta. I take the partial with respect to theta, I get r cosine theta delta y plus 0 delta z. Okay, so that's the partial derivative. If I want, now I want to find the magnitude of u theta. How do I do that? Maybe you remember. Remember the norm? Distance.
You dot it with itself and then take the square root.
That's right. You do the square root, right? You said that?
Yeah.
Okay. So I square this, so I'm going to get r squared sine squared theta plus r squared cosine squared theta, all to the 1/2, right? And that's going to, so I'm going to get an r that comes out, and then I get sine squared theta plus cosine squared theta, and that's the one vector I did, or the one trig identity I can remember, right? Which is 1. Okay, so that's r. So now I can write delta theta is u theta divided by the magnitude, okay, which is just going to be this guy divided by r. So I'm going to drop the r's. So now I'm going to get minus sine theta delta x plus cosine theta delta y. Okay, so, and this is A.611 in your book, right? So the procedure here, if you think about defining a coordinate system, is you define these curves. You can define the x's go to f's or f's go to x's back and forth, you define some relationship between your new coordinates that you want, okay, to how they're going to look in space, and the Cartesian coordinates. And then you need to find the basis vectors, which you can do by looking at tangents to these curves, and then, you know, normalizing it, right? And then if you go through that whole process, okay, you're not going to have to do that whole thing by hand. But if you look in your book, right, they have all of these written out for you. So I wanted you to have some idea where they came from. You just stare at these and, you know, and some of them you can get by thinking about it, looking at sort of the physical intuition. But so your book has all sorts of stuff on these, right? And they have the basis vectors. And then they also have derivatives of the basis vectors, which you're going to see in a second is really useful. Okay. So I'm not going to copy all of them down. We're not going to do them all here, but you can see in your book, you can kind of practice with one or two of these and work. All right. Any questions? I'm going to erase, well, let's see if there's any questions. It's easy. Boring. All of the above. What do you think, Andrew?
Makes sense.
Makes sense? Waiting for the shoe to drop on something better. All right. So, I wanted to point out, so notice that we just got this set of, you know, we did that same procedure. We would get out a delta R, a delta theta, and a delta phi, for example, if we did spherical coordinates, okay? If you look, you'll notice that you can write delta R, delta theta, delta phi as some matrix multiplied by delta x, delta y, delta z. Okay, and I'm not going to write out the matrix, it's in your book. Okay, they don't write it out as a matrix, they write it out as the sum, as if you did this matrix product. Okay, but this is a linear relationship between r, theta, and phi, and x, y, and z basis vectors. And so when we said that the coordinate system was linear, right, this is what we meant, right? That this basis, these basis sets are related in a one-to-one way, and there's a linear mapping, right, between them. So it's a linear relationship, okay? So you can write, you know, if you wanted to write this in sort of a more generic way, you could write this, let's say, some delta f, q dot delta x, okay? Conveniently, this matrix for an orthonormal system is an orthonormal matrix. And for an orthonormal matrix, this the inverse of Q is equal to the transpose. Okay, so this is for orthonormal. Okay, so if you want to go backwards from the XYZs into the F's or backwards and forwards, right, you just need the transpose of this matrix. So you'll notice that in your book, if you see like on page 827, okay, there's the relationships for cylindrical coordinates, and they have that relationship right there. And below it, there's another one. And if you go ahead and look at that in your book and notice, it's just a transpose. Okay, and so that's convenient. Right. Now the last thing. So the equations there are A.6-10 to A.6-. All right, just to give you a place to look at it. All right, so let's do vector algebra. And curvilinear coordinates. Okay, so because the basis vectors and all of the orthonormal curvilinear coordinates that we're talking about are orthogonal, all of the algebra is the same. So that's the good news, right? So this one's really short, all the same. But I pointed out because calculus is not going to be the same, okay? So just remember that if, for example, I have v dot w, and this is in, I did my example in cylindrical coordinates, this is still going to be VRWR plus V theta W theta plus VZ WZ. Okay, so it's still the same dot product. There's not any weird funky stuff going on. Okay, dot product's the same, the cross product's the same, double dot's the same, dyadic product's the same. Okay, so where it gets weird, okay, is not really weird, but a little harder, is in vector calculus. Okay, so and the reason it gets hard is because the unit vectors depend on space, right? Like that was the whole point of the curvilinear coordinate systems. But now when we go to take derivatives, we actually have to take derivatives of the basis vectors as well as the other things we care about. So when we go to write out these formulas like the divergence and the curl, we need to pay attention to the fact that the basis vectors dependent on space. So now we got to take into them into account in the derivatives that we're doing. Okay, so this all starts here. So all derivative operations require the del operator, right? That's really what's all going on every time we do a derivative. So we need to be able to get the del operator in the different coordinate systems. Once we have that, then we can do more math to keep going. So the del operator is defined as, it's defined in the Cartesian coordinate system as del x, or delta x d dx plus delta y d dy plus delta z d dz. Okay? So what we want to do, our goal, is to turn this gradient operator into something that's all in terms of, you know, say r theta and phi, or r theta and z, right? Depending on the system, right? We want to turn that into something that's r theta z or r theta phi. Okay, that's the goal here. So to do that, there are two parts that we need to convert. The first part is the deltas, right? We need to go from the delta x's to the delta r's, thetas, and phis. We just did that part, okay? So we'll write that up. Part one, we need to take the delta x's, etc., into the delta r, etc. Okay, we did that part. So part two, okay, is we need to turn the derivatives into derivatives with respect to r theta and phi, or r theta and phi. So this is the derivatives. Okay, so how are we going to get those derivatives? So the answer to that is the chain rule. Right? So in calculus, we know how to take derivatives and express them in terms of other derivatives. That's the chain rule. So the chain rule says if I have a derivative with respect to x, I want to say, well, let's say I'm going to do cylindrical coordinates here. So I have dr dx dr plus, right? So I get all the parts that come from the r dependence. So I say plus all the stuff that comes from the theta. Theta plus all the parts that come from z. Okay, so this is the chain rule for x, right? Then I have to write another one for y, another one for z. So I'm going to write that up, but I'm not going to narrate it super detailed, but I'll try and say it. d dy is equal to dr dy d dr plus d theta dy d theta plus dz dy dz, and then dp is equal to dr dz plus theta dz dz or theta theta plus dz dz dz. Okay, so we have the chain rule. Okay, and again we're going to go back to our relationships between r and r theta and z and x, y, and z. Right. So this was in some coordinates, by the way, right? So we're going to use our relationships. Say r equals the square root of x squared plus y squared. Okay, and plug that in to that one, and that one, right? And get out the relationships. Okay, so we'll do a quick example to see how this goes. So, a really quick example. If I take this one, if I do this guy right here, dr dx, how do I do that? I do dr dx. This is going to give me x squared plus y squared to the, this is 1/2, so it should be minus 1/2, right? Divided by, like x, like a 1/2 out front. And then I have to multiply by the inside, which is 2x. Is that right? Did I do that chain rule right on that one? Okay. And then I can simplify this. This x squared plus y squared to the minus 1/2. I know x squared plus y squared is r squared, right? So if I have to plug these back in to get r theta and phi, right? I don't want it back in terms of x, y, and z. So that's going to be r squared on the bottom, take the square root. So that's going to be 1 over r. So that's going to be x over r. And x I know is r cosine theta divided by r. So this actually gives me cosine theta. Okay? And so on. Yes?
Where the, oh, never mind. It's just, all right, I got it.
Yeah. So, okay. So the great news for you is that Bergstrom and Lightfoot also do this for you. Okay? So you have this in the table too. So okay, so this is what equation 8.6-7 to 8.6-9 and 8.6-25 to 8.6-27. Okay, so we are pretty much out of time and we are almost at the end. So what we are going to do is we're going to leave a little cliffhanger. Okay, we'll finish this up at the beginning of next time and then we'll launch into momentum equation stuff. Okay, you have one homework problem that relies on doing this next thing. So I'm going to give you the quick and dirty picture so that if you want, you can try and start those problems. Okay, but then next time we'll wrap it up. Okay, and the homework's not due till Monday, so you still have a chance to work on it. Okay, so the basic idea is that once you write down these, you can use this and you can rewrite the gradient. Okay, and you'll find those formulas in BERT as well. Okay, but then the problem is you're going to need to do things like del dot operation. Okay, so you want to do something like del dot v. And when you go to write down del dot v, right, v is going to be in terms of del r, del theta, del z, for example. And so when you go through and do that operation del dot v, that del r you need to take into account in the derivative, right? So when you expand that out, you're going to have something like a dr of terms that have delta r from this guy dotted with a delta r. I guess the delta r is usually out here like this. Delta r dotted with a delta r on the inside, and then whatever say vr. Okay, and so if this delta r here depends on r, you can't just pull it out, right? You have to take that into account. And so the homework problem that you have to do is to do the derivations of these different expressions so that you know where they come from and so that you can use them intelligently, right? And the trick to all these problems is to make sure that you write this out carefully and then remember to take these derivatives. Okay, so we'll do this again next time. We'll talk a little bit about more of this in detail. But I just wanted to give you a flavor so that you could start those problems if you feel like you can handle it. Okay, so I think that's all I have for you. So have fun.